Imagine a cosmic ballet, but one where the dance ends in utter annihilation. We are talking about a star, a beacon of light and life, meeting its end at the gravitational marv of a supermassive black hole. This isn't just a collision, it's a brutal, one-sided event of unimaginable power. The star doesn't just fall in, it crosses an invisible boundary, a point of no return known as the tidal radius. Here, the black hole's gravity becomes so overwhelmingly powerful that it begins to tear the star apart. It's a force unlike anything we experience on Earth. The ultimate fate of the star is a process so extreme, so bizarre, that it has its own chilling name: spaghettification. This isn't just a scientific term, it's a vivid description of a star being stretched and shredded into a long, thin strand of plasma. To truly grasp the magnitude of this event, we must first understand the two main players in this cosmic drama. Each is a titan in its own right, but one holds an undeniable, crushing advantage. Our first contender is the star, a celestial body much like our own Sunday. It's a self-sustaining furnace, burning brightly for billions of years, fueled by nuclear fusion. This incredible process generates immense pressure, pushing outwards against the star's own immense gravity. This delicate balance, this cosmic tug-of-war, is what maintains the star's spherical shape and its stable existence. It's a testament to the power of fusion, keeping the star from collapsing under its own weight. Now, meet the other contender, the supermassive black hole. These cosmic behemoths reside at the centers of most galaxies, including our own Milky Way. They weigh millions, even billions, of times the mass of our Sun. Their event horizon is the ultimate point of no return, a boundary beyond which nothing, not even light, can escape. But for a star, the danger begins even before it reaches this final threshold. The critical boundary for a star is the tidal radius. This is where the black hole's differential gravity, the difference in gravitational pull across the star's body, becomes strong enough to overcome the star's internal forces. The stage is set, the players are in position, and the star begins its terrifying journey towards oblivion. This is where the true drama unfolds, a cosmic spectacle of destruction. As the star draws closer to the supermassive black hole, its acceleration becomes immense. It plunges inward, picking up speed at an astonishing rate, pulled by an irresistible force. The black hole's gravity doesn't just pull, it distorts. The star, once a perfect skier, begins to stretch and deform, elongating into what astronomers describe as a cosmic football. Inside the star, temperatures soar to unimaginable levels as its material is compressed and stretched. The star's internal forces, the very pressure that held it together for eons, struggle valiantly against the overwhelming external pull. But it's a losing battle. The star's own gravity, the force that once maintained its integrity, finally fails. The internal bonds holding it together rupture, signaling the beginning of the end. This is where spaghettification truly takes hold, a process as terrifying as its name suggests. The tidal forces are terrifyingly efficient, stretching and elongating objects into thin, elongated strands. The star ruptures violently and catastrophically, tearing apart with an explosive release of energy. It's not a gentle unraveling, but a sudden, cataclysmic event. The star's dense core, once the heart of its fusion engine, collapses into a thin, dense stream of superheated plasma. It's like squeezing a giant sponge until only a thin ribbon remains. Meanwhile, the star's outer layers are flung outward in a spectacular spray of superheated plasma. This material is ejected with incredible force, creating a dazzling, albeit tragic, cosmic fireworks display. The star is gone, but its demise leaves behind a spectacular legacy. This is not the end of the story, but the beginning of a new, brilliant chapter known as a tidal disruption event. Roughly half of the shredded stellar material is ejected away from the black hole, escaping its immediate grasp. This material will eventually dissipate into the vastness of space. The other half, however, remains gravitationally bound to the black hole. This material collides with itself, creating immense friction and heat, eventually forming a new, superheated accretion disk. This newly formed disk heats to millions of degrees, glowing with an intense brilliance. It emits powerful X-rays, a signature of the extreme temperatures and energies at play. These tidal disruption events, or TDEs, are incredibly luminous. For weeks or even months, they can outshine an entire galaxy, temporarily becoming the brightest object in their cosmic neighborhood. Observable phenomena include a brilliant flare of light, a sudden burst of energy that announces the star's destruction. We also see thermal echoes from heated dust, glowing in the aftermath. Sometimes, powerful jets of plasma squirt out along the black hole's spin axis. These relativistic jets are collimated beams of matter and energy, traveling at incredible speeds. These jets move near the speed of light, acting as cosmic beacons. They announce the event to the cosmos, sending signals across vast intergalactic distances. In this cosmic feast, the black hole is the ultimate consumer, but not everything is devoured. There's a complex interplay of consumption and dispersal. Approximately 80% of the star's mass is ultimately consumed by the black hole. This material crosses the event horizon, adding to the black hole's already immense mass. The remaining 20% forms a chaotic, asymmetric disk of gas and dust. This isn't a perfectly ordered structure, but a turbulent, swirling remnant of the star. This remnant disk slowly feeds the black hole over time, like a lingering meal. This extended feeding process is what prolongs the light show, keeping the TDE visible for longer periods. As the black hole consumes this material, it grows slightly, increasing its mass. This process also bathes nearby systems in intense X-rays and ultraviolet radiation, impacting their environments. Astronomers are not just passive observers of these cosmic catastrophes, they are detectives, piecing together clues from across the universe. These events are invaluable scientific laboratories. Astronomers call these spectacular events tidal disruption events, or TDEs. They are a relatively new and exciting field of study, offering unique insights into black hole physics. TDEs provide critical data on black hole mass, allowing us to weigh these invisible giants. They also help us understand their spin rates and the complex physics of accretion, how matter falls into a black hole. Beyond stars, the disruption of neutron stars can generate powerful gravitational waves. These ripples in spacetime are detectable by observatories like LIGO and Virgo, opening a new window into the universe. Combining light and gravitational wave signatures from these events offers a powerful way to test Einstein's theory of general relativity under the most extreme conditions imaginable. Tidal disruption events are more than just cosmic fireworks, they are crucial laboratories for understanding the universe. They offer unique opportunities for scientific discovery. TDEs offer a rare, fast-forward view of processes that normally take millions of years to unfold. We get to witness stellar evolution and black hole feeding in a compressed, dramatic timeline. Studying the light curves and spectra of TDEs helps us measure the black hole's spin and its efficiency in converting infalling matter into energy. This tells us about the black hole's fundamental properties. TDEs also contribute significantly to our understanding of galaxy evolution. The activity of supermassive black holes, including TDEs, plays a role in shaping their host galaxies. Finally, these events help us sense otherwise dormant and undetectable supermassive black holes. When a star is disrupted, it lights up the black hole, revealing its presence to our telescopes.